Welcome to Chaos Orchestra episode number 8, Knowledge Graph Learning. Typical machine learning deployments work pretty well with Euclidean data or low dimensionality data that can easily be transformed into numbers and vectors. But more and more of our knowledge is aggregated in multidimensional complex networks or graphs. And classical machine learning algorithms struggle to use this kind of data because knowledge graphs do not exist in Euclidean space. Graph neural networks, on the other hand, were designed to work with exactly these kinds of data. The intuition of graph neural networks is that nodes are naturally defined by their neighbors and their relations, and this kind of structural information is as important as the key value pairs that describe the node. Our today's guest is Guiseppe Futia, who is an expert in graph machine learning and a research scientist at Nexa. We're going to talk about the differences to classical machine learning approaches and whether graph neural networks can be applied to semantic knowledge graphs that have complex and dynamic data models. Furthermore, we're going to talk about the data loss when encoding these complex graph structures, but also of all the possibilities and opportunities that we have when being able to learn on complex graph data. Guiseppe is very interesting to talk to, and I hope you enjoy the conversation as much as I did. Guiseppe, what is graph learning?
Graph learning includes a set of techniques in order to learn information from graph structure data. So as you probably know, deep learning has reached a huge impact in classification and prediction in a lot of tasks, and exploiting specific data, for instance, images or text and etc. But in this specific case, in the case of images and text, you have a prior knowledge on the representation of the data, because images can be represented as a grid, while text can be represented as sequences. And deep learning techniques worked very well on this type of data. And these techniques are very complex in the case of graph, because in the case of graph structure data, you have no notion, for instance, of a beginning and end of the data. You have notion of top or down. You have this complex structure. And for instance, you have to adapt these deep learning techniques on graph. And graph learning or graph representation learning is its main goal is to learn a vector representation for nodes and edges of the graph. And when you are able to map the discrete representation of a graph into an embedding space in a vector, you can apply this new learner representation for different tasks. For instance, you can predict the label of a node, and this is particularly useful for classification tasks. Or in many cases, you want to predict the most plausible relation between two different nodes. And this task is particularly interesting because it encounters a lot of application in the real world, because for instance, for predicting social network connections or for predicting protein interactions, you need this type of techniques. And there are also a lot of other applications. For instance, in the case of recommendation systems, if you want to recommend a movie or a job or I don't know, a jeans on Zalando, you can exploit this type of techniques exploiting graph learning. So these are very powerful tool to resolve this type of tasks.
So you talked about label prediction and link prediction. Is it also possible to learn on top of semantic graphs, considering the ontology and the structure of classes and relation classifications and things like that?
Yes, it's possible, and maybe knowledge graphs are one of the most interesting graph structure, because in this case, we are using knowledge graphs, we are able to incorporate human knowledge into intelligent systems. So we can apply graph neural networks and graph representation learning on top of knowledge graphs. But we have to consider that in case of knowledge graphs, you can have multiple relations between different nodes. And these relations have a specific label that is able to convey a specific semantics. So when you analyze this type of data structure using graph neural networks, you have to consider these 2 points, because in the most of the approach developed from the research community for graph representation learning, they usually consider much more simple structures. So a unique edge between 2 different nodes, no labels for these edges. So in this case, you have to consider that in knowledge graphs, you have this type of features in the representation. And in this specific case, the main idea behind graph neural networks for knowledge graphs and in general for other graph structured data is to aggregate into the node representation the representation of its neighbors. So the main idea is that at the end of the propagation in the network, a single node will incorporate its representation, but also the representation of its neighbors. And then you can exploit this updated representation to perform the tasks that we mentioned before. So for instance, the link prediction. And also in the case of knowledge graphs. Classical neural networks are very powerful, as I mentioned before, for data in which you have a well-defined structure. So in the case of images, you have a grid structure. And for instance, implementations such as convolutional networks have demonstrated they're powerful for analyzing this type of data in which you have a very well-defined structure. In the case of graph neural networks, the network should adapt to the topology of the graph. And in case of the graphs, you cannot predict the basic structure, because you can have a lot of different dimensions, etc. So the main idea is that traditional neural networks can be adapted to data that are characterized by a well-known representation, while in case of graph neural networks, the representation, in case of graph neural networks, these techniques are able to adapt to the topology of the graph. So they are able to follow the topology of the graphs, and as a consequence, analyze better, because they are able to encode this structure.
So what kinds of things can we encode? Well, what do you mean by topology?
In general, with topology, we say the structure, the local structure of a node. The main idea is that with one layer of graph neural network, we are able to encode the local structure at the first level of the node, so the most closest neighbors, let me say. And when you add different layers to the network, you are able to encode neighbors that are not so close to the central node, but they are in some way away from the node. So the main idea is if you stack different layers, you are able to encode a larger structure of the local graph structure represented by the node. So,
is there any information loss in this encoding and decoding process?
Yes, and a lot of research is dedicated to gain information during the transformation from the structure of the knowledge graphs to the representation achieved with the graph neural networks. Because in the case of graph neural networks, in the much more in the simplest architectures, you are not able to really encode the structure of the local structure of the node, because in many ways, in many cases, you just aggregate the information of the neighbor nodes to the central node, but you are not you have no notion on the real structure. Mm-hmm. So for instance, so in order to address this specific problem, one of the much more recent implementation of graph neural networks try to embed the representation of the knowledge graph in an hyperbolic space. And in the case of an hyperbolic space, you are able to maintain some information, because in the case of hyperbolic spaces, they are an extension of the tree structures. So in this case, you are able to maintain this type of information also in the embedding space, so also in the vectors, and you can exploit this information for specific tasks.
Since graph neural networks basically store information about patterns they found in this knowledge graphs, right? And what we do with reasoning rules is we define specific patterns for the inference engine to search for and to deduce new information from it. Isn't it on an abstract level basically the same, with maybe the difference that a graph neural network is able to work with probabilities and a reasoning engine is not?
Yeah, as you correctly said, graph neural networks exploit, as other machine learning techniques, statistics in order to identify patterns in the knowledge graphs in any other graph structures. The issue in this type of process, in this type of optimization process, is that you are not able to analyze and understand what happens during the training process, during the learning process in a graph neural networks. On the other side, in the case of reasoning that can be applied to ontologies, you are able to interpret what happens under the hood, because in case of knowledge graphs, you have, let me say, simple facts that describe the world, and you have the ontology that describe the rules that can be applied to these facts. And the combination between these two elements provide you results of the reasoning. So you are able to predict all possible reasoning results exploiting these two elements. So they are different for this type of learning process, because in the case of machine learning graph neural networks, you have an optimization process that exploits statistics in order to identify patterns, while on the other case, you have a description of the world using facts, and you have rules of the ontology for predicting patterns that can be completely and fully interpretable. And that's a very interesting point in my opinion.
Do you see graph neural networks being interpretable and being able to explain why links and node labels have been suggested in near future?
One of the main problems of graph neural networks, but also in general of other deep learning techniques, is that they are not interpretable, so you are not able to apply them for in specific domains that the interpretation of the data and in the interpretation of the results is one of the most important points, because if you think about application in justice or application in medicine, you have to make interpretable this type of models. And I think that knowledge graphs can help in that direction, because their capacity of reasoning will be, I think, in some way incorporated directly into the machine learning model, and then it can help to provide some interpretation on the results, and also interpretation on how the model works.
Okay, can you explain a bit more? So how would you combine reasoning with machine learning on top of the graph?
Well, in general, a very basic level of interpretation can be applied, for instance, in the case of limb prediction on the output of a graph neural network, because when you introduce a semantic level, you can understand if the output of the neural network is coherent or not. I try to provide you an example. I recently worked on the knowledge graphs built on top of publications of Politecnico di Torino, so of my university. And the main idea was to create knowledge graphs and then apply graph neural networks in order to provide new interesting information. For instance, to provide and to suggest new opportunities, new collaboration opportunities between researchers in order to create also between researchers that have never been co-authors of the same papers. So interesting suggestions. And if we only consider the output of a graph neural networks, the graph neural networks try to assign a score to any possible links of the knowledge graphs. For instance, it try to assign a score also for the prediction a paper is co-author of another paper, and it does not have sense from a semantic point of view. So in this case, you can exploit knowledge graphs in order to drive the score assignment and the prediction, because we can say it can suggest to the graph neural networks, well, this prediction has no sense from a semantic point of view. So you cannot, it's not useful that you analyze and you try to calculate the score for this type of link. So this is a very basic way in which we can incorporate the semantic information provided by the knowledge graphs into the result of a graph neural networks.
Yeah, so the thing is that building reasoning rules, like all of ontology engineering, is a very manual process nowadays, right? And not really scalable. So if we could use graph neural networks to suggest reasoning rules, that would be really boosting the ontology engineering process, right?
Yeah, I totally agree with this point. In fact, a very recent research direction is try to in some way influence reasoning rules exploiting graph neural networks. And that's also an interesting point, because it can add a step also for machine learning explainability, interpretability, because if we are able to influence reasoning results using graph neural networks, we are able also to provide information and meta information, let me say, on these results, because the reasoning is a logic, as a logic. There is a logic behind the reasoning, so this logic can be interpretable and understandable by human beings. So the combination between the neural and symbolic techniques is a very important research directions, also for the interpretability, for instance.
So we just talked about using machine learning for knowledge graph construction, or to be more precise, knowledge graph enrichment. Now, there's another thing that might be becoming very complex in knowledge graph engineering, which is connecting knowledge graphs from different domains, modeled by different people with maybe even slightly different models. Can machine learning help in creating connections and combining these different knowledge graphs?
I believe so, because the tasks that you mentioned can be also known as ontology alignment, right? So align two different ontologies that describe maybe two different domains, but have some common relations and some common points. I think that this specific task can be also, let me say, tackled using graph neural networks, because the main idea is always to create a relation, right? So a relation between two different classes of ontologies, or a relations between two different relations. And if both the ontologies are, let me say, enough rich in terms of semantics, I think that it's possible. And the main interesting thing is you can also exploit the instances, so the data that are modeled using these ontologies, and they can provide also further information that can be exploited by the graph neural networks in order to infer this relationship between the different schemas. So you can exploit both in these cases. In the case of machine learning, traditionally, it's quite complex to manage evolving data. So in the case of knowledge graphs, you get the point, because the powerful and the strength of knowledge graphs is to they are able to evolve in the time according to the evolution of the domain. And I saw that there are a lot of research also in the direction of temporal graph neural networks. So graph neural networks that are able to resolve and try to predict also the evolution of the graphs during the time. I know that, for instance, Twitter Twitter currently is doing a lot of research in this direction, because as you know, in that case, you have social networks that evolve in the time, and but actually they are much more focused on the instances of the data. And maybe an interesting relation, an interesting research direction would be the analysis of the evolution of the ontology during the time. I think that you identified a good research direction for the future, because I did not see a lot of papers, a lot of articles, a lot of contributions for this specific task. So for analyzing the evolution of the knowledge graphs in terms of schema and not only in terms of data.
So Giuseppe, what do you think how a perfect system in the future might look like, given this strength of knowledge graphs to be able to handle evolving data, and this lack of possibilities with neural networks to represent evolving data?
We should identify what is the best way in order to map the knowledge graphs information, the knowledge graph structure into the neural network. Because if you're able to map the knowledge graph information on all the architectural traditional deep neural networks, so on the input data, on the internal layers and units, on the output data, we were able to create a system that is able to exploit the powerful in terms of classification and prediction of deep learning techniques, but at the same time is a system that is able to interact with the human being. So for instance, with the domain expert, in order to explain its results, and also to propose suggestions for, I don't know, other type of analysis. Because I think that the last point, let me say, evolution of a artificial intelligence system is not only a basic interaction with the human being. So in general, the human being can make questions and the system try to respond to this question. But I expect a development in which the artificial intelligence system itself is able to provide suggestions and provide also a new direction to the human being. And maybe the human being have never thought before to this type of suggestions and direction. So I expected as the combination between the knowledge graphs and the deep learning techniques can, let me say, can provide, this type of evolutionary systems.
Mm-hmm. How do you connect that? If you have the data represented in the knowledge graph and the data that is learned on top of the knowledge graph, I mean, how do you bring that together? And is that even the best way to represent knowledge? I mean, maybe knowledge graphs is just a human way to represent knowledge, and in systems where AI doesn't need human interaction, maybe our data models and meta models are just inefficient to represent kinds of knowledge.
Some tools maybe do not need a deep interaction with the human being, but the information that comes from relations can be exploited anyway, because this information is in some way encoded in the knowledge graphs, and this information is encoded because we have some expectation, so we want to exploit this type of relations. In case of graph neural networks or machine learning techniques, you have a direct notion of this relation in terms of human understanding, but this relation is also a data point that can be exploited as information for learning prediction and for learning new other information for other tasks.